Alrighty, 1.8, valence electrons and ionic compounds. So obviously I'm going to review a little bit of stuff we've already mentioned, but it's always good to review, you know? So, we have ionic, it's a metal or non-metal, or we have those polyatomic ions, you know. It's always going to be something positive with something negative, so technically it also could be two polyatomic ions. Again, really depends on whatever you're combining. One of the things lost electrons, one of the things gained valence electrons, and so we know this based off the periodic table. We want to fill the outermost shell, and so I'll show a couple examples of, well, one example of that in particular. And so for ionic compounds specifically, you're forming these bonds based off of those valence electrons, and again, you're either losing or gaining them, and the nuclei of the elements will either, take it in or give it away. Again, it depends on which one is which. There's a lot of factors involved in deciding it. So let's look at potassium chloride. So potassium is K, right over here, and then chloride is over here. And so let's think of gas notation, electron configurations for both of these. So we have potassium. So potassium is going to be argon. Actually, let me write it down. K. So argon, and then 1, 2, 3, 4. So 4s1. And then chloride ion, or not ion yet, just chlorine. Let's see, we got neon. And then it'll be 3s2. And then 3p, 1, 2, 3, 4, 5. Cool. And so in order for these to become ionic, you want to gain or lose electrons depending on the orbitals being filled. And so looking at these two options, for potassium, I could lose this electron here, and it will have a full valence, because if I look at argon, argon would be, let's see, 3s2, 3p6, and so that would be a full valence shell. And then for chlorine, I can gain one more electron to make this 3p6, and so then that would be entirely filled in the energy level 3, and so the valence electrons would be filled by gaining an electron. So again, potassium would lose an electron, chlorine would gain one and become chloride, and so just to reiterate that with the electron configuration of those here. So potassium is going to, I can't write argon in brackets and then do that as gas notation, so I have to go one before it. So neon, and then 3s2, 3p6. Chloride ion would therefore be neon, 3s2, 3p6. And so this is why potassium is going to be positive, because again, the valence is going to be filled by losing this guy, and then chloride, it's going to be filled by gaining one more electron, and then all of the valence is filled. And so these two can form a ionic bond, and so there we go. So it's all about the valence electrons, it's all about the gas notations. And so as a reminder, I told you about that trend where period 1 is +1, this is +2, +3, and so on. It's all based off gas notation electron configuration. So we could see why we're gaining or losing electrons purely based off that. Okay, so there's a term called analogous compounds. It sounds complicated, but it's a lot simpler than what it means. So families, in case you forgot what a family is, on your periodic table, it is a column. So this would be group is a family, this is a family, that's a family, and so on and so forth. So you read that in the summer homework. And so you would make compounds that are similar if they're in the same family. So looking at, for example, beryllium's here in group 2, magnesium is also, calcium is also. And so they're all combining with fluoride ion. So fluoride ion is -1, this whole column is +2, so the formula unit for this would be BeF2, and then for magnesium it would be MgF2, calcium would be CaF2, and so on. So within a family, they're going to make the same ratio for that formula unit. And so, you know, that's all it means. That really is all it means. Just a fancy word for it. Again, the charges of the ionic compounds, like this example I did here, look at the periodic table. You can follow the trend that I talked about way back when, and then the valence electrons in the electron configuration will show you why it gains or loses electrons in ionic compounds. Remember, specifically talking about ionic compounds. Okay, and so the crystal lattice, aka solid, of the ionic compounds look something like this. So, for example, this sphere could be sodium, and then this sphere could be chloride ions, and so you could see it follows a pattern going up, down, left, right, and in 3D. And then this would also be another example in 3D of magnesium and chlorine, and so that would be another example. So again, just think of these in 3D when they exist. They're all, in this chunky, weird cubic thing, and there we go. And so this arrangement, the way it works with this alternating positive and negative bits, no matter which one we're looking at, it's going to tell us a lot of information. So we're going to know about solubility, which will be later on, I think, or maybe this section, I can't remember. And then melting and boiling point, which we'll definitely talk about this section. We have electrostatic forces, which is represented by capital F subscript E, aka a Coulomb force. So we're going to talk about, Coulomb's law that we've been talking about, like last section, for example. And so these crystal lattices are super duper strong because, again, opposite ions are attracting. We have these ionic bonds happening between the cation and the anion. And so because they're so strong, then we have a strong electrostatic force, or a Coulomb force. Either way. I've seen both used on College Board's tests, so make sure to know both. You need more energy to break these kind of bonds. So, like in general, ionic compounds have very high melting and boiling points because there's a lot of energy here, because again, it has strong electrostatic forces. Alrighty. So, why did I make this transition? Okay. So, here's your turn. So in order to strengthen bonds, we can increase the charge or decrease the size. So using Coulomb's law, make sure you're able to explain both scenarios, and then I'll talk about it in a few moments. So pause this video, try it out. Okay. So in order to strengthen these bonds, these ion bonds, if we increase the charge, looking here, we're going to decrease distance because increasing charge means there's more attraction between positive and negative things, and so the distance will decrease, and then that force of attraction increases, the electrostatic force increases. So the electrostatic force that I talked about earlier, that would be represented by F here, just with a little subscript E. That's all. Cool. And then for decreasing size, so if I decrease the atomic radius, specifically, because that's what we could potentially do, then the, the nucleus from one atom and the valence electrons of the other atom could get closer together, and so that would increase the force of attraction. Okay, so there we go. So like I said a couple times already, cation is the positive ion, anion is the negative. The way that I remember is the letter T looks like a plus sign, so positive. You can also think of cat. Cats have paws. Positive. Whatever works for you in memorizing stuff, I use dumb ways to memorize things. Okay, so other reminders from Gen Chem / middle school. Melting point is when you are going from a solid to a liquid, or if we're going the opposite. Now, sometimes it's called freezing point when we're going the opposite, but it's the same value. So you can say melting point even if you mean going the opposite direction. So again, melting point's going from solid to liquid and liquid to solid. And so boiling point is going from a liquid to a gas or a gas to the liquid. And then in terms of energy and temperature, you need to know, am I inputting energy in order to change phase, or am I releasing energy? And so temperature, it's at a set temperature depending on whatever compound or anything that you're talking about. And for energy, well, you have to think, am I going to be making or breaking interactions between stuff? And so you want to think about what kinds of things that you are going to be making or breaking. Now, I will say that we will focus more on that, I believe, in Unit 3, so I won't hardcore talk about it now, but we do need to think about those interactions and which one is inputting energy versus not inputting energy. So, yeah, it'll be a future unit, but we'll get there. Okay, so here's an example of an ionic compound. Or two, rather, sodium chloride and magnesium oxide. And you can see here the melting point is significantly bigger on magnesium oxide, and the boiling point is also significantly bigger. So how can I explain why magnesium oxide has a bigger melting point and a bigger boiling point compared to sodium chloride? So I'm going to use Coulomb's law, so that's why I have it up here, to explain that. Again, Coulomb's law comes in clutch. It's very good at explaining a lot of different things. And so I think about, first of all, let's just circle where these are on the periodic table. Okay, so sodium is over here. And then, can I use a different color? Oh, it won't let me. Okay. So sodium there, chloride, yellow on yellow, that's not handy. So chloride's over here, we got magnesium over here, we got oxide over here. Okay, so we can think about many ways for this. So we can think about the proton amount for both of them. And so you could see magnesium and oxygen have 8 protons and 12 protons, so that's pretty good. Sodium and chloride have 17 and 11. So the amount of protons aren't the reason why magnesium oxide is greater in melting point and boiling point, because chloride has so much more compared to magnesium and oxygen. So it can't be because of the proton number specifically. But we can think about, for example, the atomic radii and how they're going to interact from one thing to another thing. So magnesium and sodium, they're both in the third energy level when I think about Bohr's model. And so, that's great. And then chloride is also in energy level 3, so that's far away. Versus oxygen, oxygen is in the second energy level. So if I think about oxygen here, so this is going to be oxygen, and then I think about magnesium, so magnesium is going to be 1, 2, 3. I'm not drawing the electrons because I'm lazy. Cool. And then versus sodium, so 1, 2, 3, and then chlorine, 1, 2, 3. So what is attracting in an ionic compound besides the charges? Obviously we have the nucleus from magnesium, right here, and then we have the valence electrons on oxygen. So remember, there's one less energy level, so that's going to be closer together compared to, here and this outermost one, because there's 3 layers versus 2 layers. So that makes a huge difference right there. Then we also can go the opposite direction. So I go from the oxygen nucleus to the outermost one on magnesium versus the chloride nucleus and the sodium valence electrons. And so, again, distance, the oxygen is smaller. And so because we have a smaller atomic radius here on oxygen compared to chloride, chloride ion, and so that's the main thing. Now, if I had to write this for an FRQ, I would talk about the ion's nucleus of one atom to the valence electrons of the other. So I would talk about the nucleus of magnesium being attracted to the valence of oxygen and how that distance is going to be less compared to the the sodium nucleus to the chloride valence electrons. So that's how I would personally explain it. You could also mention charges in general. So you could talk about the +2 and -2 versus the +1 and -1. Having these two different charges for the whole atom, having a bigger charge means more attraction, more electrostatic forces as well. So you can also talk about charges. Both are good to mention in an FRQ problem. And so when I have a stronger ionic bond, I would have a stronger or a higher melting point and a higher boiling point. So mentioning that as well. So talk about Coulomb's law, then talk about how you're making a stronger ionic bond, and then therefore we'll have higher melting point or higher boiling point. Okay, so here are 3 examples. Boom, boom, boom. And you pick which one's going to have the highest melting point and why. Things to think about, so think about those things. Alrighty, so pause the video, try it out, and then I'll show you the answers in a few moments. Okay, so there we go. If you have questions, let me know. Otherwise, there's your answers. I didn't explain why, though, so make sure you explain why. Use Coulomb's law and stuff. Yeah. Alrighty, so pretty much this section is just, use Coulomb's law effectively. You don't need to memorize stuff unless you want to. It does help, to recall faster, like periodic trends, for example, knowing Coulomb's law and how to use it. But again, technically it's not needing to be memorized if you can understand the logic behind it, but that's up to you. Okay, that's it for this section and for the unit, besides whatever I have to cover in class if I haven't finished stuff by the time you're watching this. Okay, bye!